Hi, my name is Zachary Lyons, and this is my black hole lab number 3 for Physics 2211, Introductory to Physics 1. In this lab, there will be two parts. In the first part, I will be finding the mass of a unique black hole and simulating the curved motion of a star orbiting that black hole using a computational model, as well as Newton's second law and the perpendicular and parallel components of the net force. In the second part of this lab, I'll be finding the initial velocity of a spaceship whose trajectory gets very, very close to the black hole, but escapes the black hole without crashing into it. I'll be using the following formulas in this lab, specifically the net force equation from Newton's second law, which states that the net force on an object is equivalent to the change in momentum of the object over the change in time. I will also use the velocity update formula and position update formula derived from Newton's second law in order to update the star and the spaceship in part 2's position and velocity over time. The net force of the object can be broken down into two components, the parallel and the perpendicular component of the net force. The parallel component of the net force acts parallel to the object's motion, and it changes the speed of the object. The perpendicular component, however, acts perpendicular to the object's motion and changes the direction of the velocity over time. The gravitational force equation was also used to find the mass of the black hole and was used to find the net force acting on the planet as well as the spaceship in part 2 of this lab. The equations shown on the previous slide were modeled using code, and as seen here to the right, they were converted into a computational model representing the net force, which is just the change in momentum over change in time, as well as the parallel and perpendicular components. The mass of the black hole equation was found using the universal gravitational equation and is shown on the bottom line. The initial conditions for this lab, the mass of the star is constant at 2 times 10 to the 30 kilograms, and the universal gravitational constant does not change at 6.7 times 10 to the negative 11th. The surroundings for this part of the lab is the black hole, and it acts on the system, which is the star. Shown here in the model to the right, once the code is run, the orbit is shown here with the following arrows. The orange arrow is the net force of the object acting towards the black hole, and the net force, the parallel component of the net force, is shown by the magenta arrow. The cyan arrow is the net force of the perpendicular component. The mass of the black hole after the code was run was found to be 9.297632 times 10 to the 33rd kilograms. This mass was randomly generated when I input my school email into the starter code, and it randomly generated that mass for the black hole. In the next part of the lab, I was finding the initial velocity of the spaceship that would require it to get super close to the black hole but not collide into it. The mass of the black hole is consistent with that of the first part of the lab, and the mass of the planet was 9 times 10 to the 29 kilograms, and the mass of the ship is 7 times 10 to the 10th kilograms, and these did not change throughout this part of the lab. The X and Y components of the ship's initial velocity was found using trial and error, using the trajectory that was simulated by the code, where I could see it getting closer and closer to the black hole and it not colliding. Using the universal gravitational force equations, I was able to find the force on the planet by the black hole, as well as the force on the planet by the ship, and the force on the ship by the black hole, and the force on the ship by the planet. These are modeled here using the universal gravitational equation. Then I updated the planet's position and velocity, as well as the ship's position and velocity, using the position update formula, as well as the velocity update formula. And once this code was run, this was sped up for time's sake, but you can see that the trajectory of the spaceship shown by the magenta line gets extremely, extremely close to the black hole, yet it does not collide with it and escapes its path. So how are the net force, the parallel and perpendicular components of the force different from the rate of change momentum and the parallel and perpendicular components of the momentum? These are the same quantities, it's just that there's different calculation methods to find them. Since the net force is equivalent to the change in momentum over the change in time, and this equation, or this formula, requires the mass of the black hole to be found, it's used to calculate the net force, which is then used to find the rate of change of momentum, which allows us to calculate all components of the net force. Then, to find the initial velocity of the spaceship needed to enter an orbit around the black hole, this was also found using trial and error, but this initial velocity is negative 8 times 10 to the 6th in the negative x direction and 8 times 10 to the 5th in the y direction. And shown in the picture, the cyan trajectory is the planet, and the trajectory of the spaceship is shown magenta, but they both orbit in a circular motion. And I forgot to mention, but in part two, the initial velocity of the ship's speed in order for it to not collide with the spaceship was negative 3.6 times 10 to the 7th in the negative x direction, as well as 1.35 times 10 to the 6th in the y direction, meters per second. Thank you.